Welcome to a new test and teardown video. This time it's another Hewlett-Packard. This is the model 608E VHF signal generator. It covers 10 to 480 megahertz, so yes, it covers a little bit more than the entire VHF frequency range. I don't know if this is easy to see here, but look at my desk. It just takes up the entire area here. This is about a half a cubic meter. This is big. And as you can imagine, with those big handles, it is a 27.6 kilo. And this size is just amazing. The basis design of this is from 1965, and it was discontinued in 1981. So I bet this one is from the about 70s. And it is a combined tube and transistor unit. So all the high voltage supplies, they are made of tubes. All the sine wave oscillators also made by tubes. And a lot of all the small signal stuff is made by transistors. Unfortunately, this one was thrown out in a dumpster some weeks ago. So we got some really nasty dents in the box. Let me see if I can show you this. So I will take it out of the box first and do a deep inspect before I power this up. It was quite easy to open this unit. In case you don't know how to do this in general, with HP equipment like this, all you have to do is take away the feet, just unscrew them, and then you can pull out the inside stuff from the case. Easy. So let's look at this wonderful machine. See, we got all the power supply parts. That's all the high voltage stuff. That's done with tubes, obviously, right? And then we got some more power supply parts down here. Main transformer, and that will be voltage, high voltage reference tubes, and of course power supply parts. And yeah, we're already inside the magic carousel switch. So for all the different frequency bands, remember I couldn't move this, but now I can. A little bit of contact 61 and a little bit of a mechanical adjustment. See, this is the kind of the groove that stops each position of the carousel switch. And the way that this piece of plastic here, or it's glass fiber filled plastic, the way that this was made, it had really sharp edges. So what I've done is I took a little blade and I cut it a little bit here on each side. So that means when this wheel go and lock down here, I can get it up again a lot easier. I mean, it was so tight, I need to probably almost use a tool to do it. It's still tough, but yeah. Oh, definitely this is not for small babies with weak fingers or something like that. But it's possible at least, right? So the carousel switch is a two-section switch. The first is the oscillator switch. And we've got some tubes up here. You probably see this tiny little part here. That is the connector that connects to the top of the tube. So the tube is here. This is a 4040 tube. Yeah, 4042 is it called. It's a triode, high frequency oscillator. tube. And it's a beautiful, beautiful tube, by the way. And so the oscillator here is then connected to a buffer amplifier. And that buffer amplifier tube is located under that bump of this lid. I don't know if I'm gonna go in there really. It's not super interesting, by the way, but then there's an output amplifier tube, and that is right there. So what you see here is the contact to the top of that tube, and that is also a 4042 tube. And the output section here is again tuned to the same frequency ranges and all that kind of stuff. The output attenuator, let me move the attenuator. Can you see what's going to happen here? Here we go. Can you see that one? That is actually the output coupler that goes in here. Okay, here we go. Can you see? What you need to look at is here, right behind my nail right now, okay? So we're looking right there, and then I move the attenuator. Can you see? This is the output coupler. Full output drive, and it goes all the way into the oscillator winding right there. And then I go a little bit back, and then I can take another output coupler. They are right here. So they, see, that is the winding here on that coil, and that is of course the coil that we connects to with the output coupler right there. And this is maximum output. By the way, this type of attenuator with this tube and this little coupler and this distance, this type of output attenuator is very, very good. And it's very simple. And of course it was an attenuator type from the 60s and 70s and all that kind of stuff. But today we use something completely different. But back then, this was definitely a very, very good solution. Super accurate and easy to make. If you wonder why this inductor here is not straight, this is normal. This is completely normal, and this is quite obvious why it is like this. This is the highest frequency range, that one winding or half a winding, right? And then this one is the lowest frequency range. And then you can of course imagine that the lowest frequency range, there will be quite a lot of field going on here, right? So to avoid coupling to that one and creating all sorts of dips on the frequency range, they of course made it like this. When you go up in a little bit higher frequencies, the field is now a lot smaller, and then there's not a problem with this coupling to the nearby inductor. Well, that is, yeah, I think that is quite funny. Yeah, inside this room here, yes, we of course have the output power coupler, but we also have a little oscillator, and there's a crystal down here. If you see this, I think I will go back to that a little bit later, probably if this unit works. But there is a little oscillator here, and there is a coupling to the output drive from all the harmonics, and this way it mixes together with the output. And you can see this on your scope, or you can listen to this on your headphones. There's a headphone jack here on the front, and that is so when you want to calibrate this or align this, when you power this up, then you simply listen for the beat, 0 beat, then you know you are at the correct megahertz, every megahertz settings. So for example, let's try and simulate this. So let's try and play with the frequency settings. Look at this little red arrow in here, right? When we change the carousel switch between the different ranges, this little arrow here follows and shows exactly what band we are in. So let's just take the first band A. That band is from 10 to 21 megahertz. They call it megacycles, but that is just to avoid saying hertz. And now we dial around here and find the frequency 15. But if you don't hear this, the 0 beat, obviously the crystal is super accurate, and all this mechanical tuning here is not accurate to the last little hertz, right? So if it beats here, and here you have your 0, it will be a little bit annoying, wouldn't it? So all you have to do is just dial this one and move the line. The line actually moves the entire glass because this line is connected to the glass. So this moves the glass, and then now it's accurate. And this unit is full of mechanical gimmicks to fix all those small things. I will show you a few more. This is the frequency adjustment. Okay, so you can imagine what happens here is that will be the two capacitors right here and right here for the oscillator and the output stage. Okay, look at that. Now they are moving, but here is the output power. This one, follow this. Hang on, let me see if I can get some better light. Yeah, that was better, right? So let's follow this the shaft here, right? Now I crank up or down the output power, and I don't know how visible this is, but see? So this, I only now move the output power. Okay? And if I leave this is the power I want. Now I change the frequency, and then it again moves the output. So everything here is auto moving and auto aligning when you're changing stuff. Isn't that just cute? And this is, you push something, there's a little, all this couldn't move. I just cleaned it a little bit with contact 61. And this is the back of the unit. Yeah, I am ready to power it up more or less. The output coupler wire is just hanging loose like this, and this is the pulley cable system for the power adjustments. See, if I move the coupler out, of course the cable follow. That's just how it is. And here we got all the different capacitors for all the different voltages and all the high voltage power supply stuff. Not super interesting. I really hope this stuff works. I want to show you the right side of the unit. This is also where you can see the pulley system for the attenuator here. Mains transformer. And this is a classic feed through entry. HP, they're using this more or less all the time. All this is auto level and all the compensation stuff for leveling, modulation levels and all that kind of stuff. Because every time you go in and out of all the different ranges, and we will get information about this from switches. So the whole compensation circuit, they are fixing all that, so we get a constant modulation and constant amplitude and correct stuff. Oh, look at that. Oh, this is tough too. Oh, this is the oscillator, the modulation oscillator, and that is done with tubes. Perhaps to make it nice and clean. They could have easily designed this using transistors to save weight and save size, but that was not the case. They really didn't care about that. They just wanted to use something they are very, very used to do. If you look at this circuit here, you can probably recognize this circuit because this is the internal parts from the very, very famous HP sine wave oscillator called 2000 CD. No, 200 CD. No, of course it is a 200. So that is more or less the circuit from that oscillator. Here is another really, really cute mechanical gimmick. This is the fine frequency. I mean, fine as in ultra insanely fine. Look what that one is doing. It is moving. This, where is it? This is the part. And it just moves around like that. And isn't that just cute? How many millihertz is this? I can't wait to play with that. So if this thing feels like blowing up, I might as well just have it on video, right? Let's crank on. Mains is now to the input section, and I don't have a leak to chassis. Everything here is on earth potential correctly and all that. So let's 300 and then 200, 155, 120, 100 and did you hear that? That was not good. Scary. But there was definitely something that said clickety click, and that is not good. And then I got scared. Let's do it again and see what happens. Okay, let's do it again. Boing. 150, 120. Then I will try and be quiet so you can hear what's going on. So because I'm super scared. But I see output. I got output. Okay. It is running. I got output, and I actually got tons of output. Yeah, my copper was at maximum. It's using 150 watts. And this is 15 megahertz, 15.1. I was trying to reach 15 exactly, so my idea is... See, I'm dialing down here on the frequencies, and then I'm just going here for 15 exactly. Fantastic. And then I will try and see if I can move. Yes, I can. So now it is calibrated. And here's the fun thing. Now I should be able to dial it to 16, and it should be super duper accurate. What do you say? This is 16, right? And it is 16.0. It is just amazing. Oh, but it's 150 watts. Let's try and look at... Oh, that is beautiful. I don't know if you can hear this, but I just put a little handy here. Can you hear it? And there's no modulation, no internal modulation. Whatever I do here. So I think we have a problem with the oscillator. The internal oscillator. I believe this is AM, by the way, and this radio is of course FM. But you can hear? Here. This is a typical mechanical. If I touch something over here. But it's really not that bad. And listen, squelch is completely open. And it's silent. Of course this is possible because it's open here. So it's that stable on the frequency. Amazing. And if I look at the readout here in the upper right, here is the frequency. You can see that it's slightly drifting. Let me try and see if I can adjust it up here to 225. Now I am on the middle of the channel. It is that stable. I did not expect it to be that good. So I've been playing a little bit around with the modulation, and as you can see here, the yellow curve is still the signal on R10 of the oscillator, and that is of course working. And then the purple curve is my RF output. So it was actually user fault, or just not knowing exactly what to do. The RF output, if I crank up too much RF output, you can of course see that it goes into total clipping, and that means there is of course no regulation, and there's also no modulation, because it all goes through the same transistor circuits. And here you can of course adjust your modulation. I could of course, so this is RF output, and then there's another one that adjusts for modulation, as you can see here. Let's look at a little bit more. So this is my modulation, see? And now it is correctly set up, so I can do it correctly, right? And then if I crank around with my RF output, see? Clipping, and then here we go, that is my maximum, and then I can play around with my modulation and achieve exactly what I want. So it's not that bad, really. So you can really do almost what you want here. Huh, that is quite nice. Now that everything seems to be working, I wanted to try and have a look at the really nice tubes that's down there. So I thought that I needed to mark the indicator here, but see, they got those pins, so I can't mount it wrong. So now we are all the way in. So this will be the oscillator tube, and that is of course the 4042 tube. Tiny little super fast triode. And that will be the filaments here at the top, and you unscrew it here, and then you can pull up this entire part here. On the other side of this part, I believe we also need to use the same tool, and here is the tool. That is nicely located here in a little rubber thing we just release here, and then you can pull this up. The idea here is that you release this and desolder the wire for the filament, and then you take the tool here, and then you can unscrew the output stage, and that is also a 4042 tube. In between them we got this buffer amplifier tube here, and that is a nice special quality gold plated tube. I really like them with the gold plate. Huh. Look at that one, is a feed through capacitor. That one, that is just beautiful. Because of course this circuit works all the way from 10 megahertz to 480 or something like that. Wasn't it 400? And yes, that is something. And that is why we got all these feed through filters for everything that needs to go in here. Yeah, except for that one, of course, but. And look at that thick, heavy, super stable casing here with all those ball bearings on everything. We got 2 ball bearings here and 2 here, and it's just absolutely top class quality. I think it's also possible to get a much better view of the power is here, and as you can see, when I'm tuning, I move both of them, and that is of course the power output, and the power is also a thing when you're doing tuning. I really love it. I really also like this little detail here about this the lid and that one for the tube. Isn't that just, oh yeah, that's just amazing. So now we'll put everything together. I'm quite happy about the way that this worked. I was a little bit skeptical because the case was badly dented, but I'm so happy to see that everything works. Oh, I forgot to show you. This is the frequency calibration screw, that one here. And see, when I turn this, I move the glass left and right. I really love these mechanical solutions to simple things. And now we have a very good access to that bulb, by the way, so it's tempting to change it. But it is actually still working, so no need to do that, right? So there's not a lot more to say. I just wanted to say that I'm very happy that I'm done playing with this one. And it is really, really fascinating. Here you can see all the different contacts. Got a little bit of a funny little detail going on over here. See those? Oh, that will be the output inductors or the output couplers. But look at the dimensions. See, it's flat on one side, and that is so it's not touching that circuit board. And of course this is the height that makes the coupling to the output coupler that shows up down here, right? So everything is perfectly carefully aligned here. So now you can enjoy this beautiful view, and I like to say thank you very much for watching, and bye bye.